Good day, everyone. Welcome to our presentation today. My name is Darren Adikarama Prajoyono, and together with my colleague, Rifki Apriansha, we are excited to present our research today.
Okay, today we will walk you through our research titled Analysis of Data Caching and Synchronization Strategies in Offline First Mobile Application. As mobile computing scales, handling the real world unpredictable of network environments remains a pivotal technical challenge. Let's look at our roadmap for today on slide 2.
We've structured our presentation to follow our research path systematically. We will start with our study's background and the core problem statement, transition to our methodology and evaluation matrix, and then deep dive into our telemetry and survey results.
We will conclude by introducing our newly developed architectural decision framework and showing you where you can access our open source code base. Rama, why don't you start us off the background?
Thank you, Rifki. Now, when software engineers and architect mobile applications today, they are faced with a challenging tug of war. On one end, they need to supply absolute data freshness, and on the other hand, they must maintain a highly responsive, low latency user interfaces. In real world environments, such as elevators, crowded transit hubs, or even rural areas, mobile applications face severe performance drops. Traditional applications often fall back on synchronous offline online fetching. This means that if a network request times out, the entire user interface locks up. These frozen screens block users and can lead to immediate app abandonment. We knew we needed a concrete, evidence based performance benchmark to help developers escape this cycle.
Building on that background, we select four critical problems in modern of mobile engineering. First, developers persistently design systems assuming internet access is stable and always available. As we know, real world conditions are highly unpredictable. Second, traditional offline first strategies like network first act as synchronous UI blockers, freezing the layout during network delay. Third, there is a constant difficult trade-off of trying to balance freshness with UI responsiveness. And finally, before the study, there was a major research gap. There was no evidence-based quantitative framework existed to help mobile developers choose the correct strategy for their system. This study directly solves the gap.
To solve this problem, we designed a highly robust, multi layered methodology. We combine quantitative system performance testing with a user experience validation survey to bridge the gap between hard system telemetry and actual user perception. First, on the development side, we built a fully functioning task management prototype built on the high performance Flutter framework using Dart. This gave us a native code base to test our repository strategies. Second, for our user survey, we developed a standalone evaluation application. We tested it on 10 to 15 real world participants who rated their perceived speed and reliability on a 5-point Likert scale immediately following state changes. This allowed us to validate our system metrics with subjective human satisfaction.
The core application logic leverages a specialized repository pattern. The repository acts as a smart decision router, abstracts local NoSQL storage from remote database structures. But to test this reliability, reliable, we could rely on unpredictable commercial ISPs. Instead, we built a programmable network throttle directly into our HTTP middleware. This allowed us to manually inject systemic latencies ranging from perfect 0 millisecond baselines on extreme 5 second 5 seconds delay as well as control pocket loss rates. This gave us perfectly sterile environment to benchmark performance without external variability. interference.
This brings us to our factorial design matrix shown on slide 7. To ensure mathematical integrity, our automated stress testing scripts ran across 7 distinct latency profiles and 5 packet loss levels. We evaluated 3 primary repository strategies, namely network first, cache first, and the hybrid stale while revalidate or SWR. By testing every single permutation with a 20-time loop replication, we recorded a total sample size of exactly 2,100 automated iterations. This massive baseline of telemetry data was logged directly to local storage to prevent data loss during offline states. Now let's dive into our results. Our telemetry data confirm our worst suspicions about traditional architectures. If you look at the charts on slide 9, as network delays climb, traditional strategies are held completely hostage.
It was a strategic bottleneck. Under maximum 5,000 milliseconds simulate delay, both network first and change first strategies essentially choke. Their average UI renders latency spiked to a brutal uh, 5003.15 milliseconds and 5002.15 milliseconds, respectively, completely freezing the screen.
But look at the SWR line plotted under bright green on the chart. It sits perfectly flat at the bottom. By asynchronously separating user interactions from network operations, the SWR strategy rendered in effectively 0 milliseconds across 2,100 iterations. It reached the NoSQL cache instantly while quietly managing network failures and timeouts in the background.
The validation survey also confirmed this. Our validation survey yielded incredibly fascinating result. Surprisingly, we discovered that human tolerance for UI latency is actually quite high when the application provides visual feedback. For example, even when change first blocked the screen, participants still gave it a respectable 3.9 out of 5 certification rating. However, when it came to the double to to the SWR strategy, the result were unmatched. SWR achieved an essentially perfect 5 out of 5 score for both perceived speed and perceived reliability from every single survey participant. This proved that instantly showing change data dramatically boosts user confidence in the system, even if the application background synchronization falling is failing.
In conclusion, our research proved that the stale while revalidate strategy provides the optimal data caching and synchronization architecture for offline first mobile applications.
By using lightweight last write wins and data synchronization, we successfully minimize bandwidth usage. Our empirical data has allowed us to craft the architectural decision frameworks shown on slide 11, giving developers an objective map to choose synchronization path based on network stability and freshness requirements.
Our prototype source code and comprehensive experimental logs are entirely open source and publicly available on the tiny URLs on the paper. We would like to extend our deepest gratitude to the Computer Science Department at Bina Nusantara University for supporting this study.
And with that, we thank you for your time.